Jai Hind to all of you. I'm Dr. Ritish Kumar. I'm going to give a lecture on communication engineering subject. The topic of the subject is frequency modulation. So, what is the frequency modulation? First, we will go through the syllabus of the university syllabus. Then we go for the in which unit we will have a frequency modulation. So this is a university syllabus. So I'm going to tell you about the unit number second, where we have a frequency modulation. You can see over here, this is frequency modulation. So this is a kind of angle modulation. Here we will cover the topic here. So here we have the all five units. So next one is the recommended books. So I preferably most recommended book here the Simon Hickel and the Tom and Sailing. You can refer uh, for the topic of frequency modulation. You can read over here, and you can find the this one is the these two books are most suitable for this topic. So here the recommended books are mentioned over here. Now the introduction. So what is the modulation? Modulation is the process where a low frequency signal can be transferred into the higher frequency signal, and by using the modulation technique, we we can travel the signal at a very far distance, irrespective to the low distance. So there are various techniques for the modulation. And in other terms, we can say modulation converts the baseband signal into the passband signal as well. So analog communication system, we have a different kind of modulation technique. The first one is the amplitude modulation, and the second one is the angle modulation. So in the amplitude modulation, we have DSP, SSP, and BSP, that is double sideband, single sideband, and vestigial sideband suppressed carrier, that we have already read in the unit number first as well. And now the angle modulation. In angle modulation, we have two kind of modulation. The first one is the frequency modulation, and second one is the phase modulation here. So these all kind of amplitude modulation and angle modulation can be characterized in the baseband modulation scheme, as we have mentioned over here. And now the second analog communication and second modulation technique in the analog communication system is the passband modulation scheme, where we have FDM, TDM, and CDM. Means frequency division multiplexing, time division multiplexing, and code division multiple, etc. So these kind of modulation action we have in the analog communication system based on the baseband modulation scheme, and second one is the passband modulation scheme as well. Now the frequency modulation comes to the point. What is the frequency modulation? Frequency modulation means it modulates the frequency, and for which signal it modulates the frequency. If I talk about the perfect definition of the frequency modulation, it modulates the frequency of carrier signal with respect to or in accordance with the instantaneous value of the message signal. So we have two kind of signal. The first one is the message signal, that is represented by AMT, and the second signal is the carrier signal, that is CT. AMT is the message signal here, and CT is the carrier signal, right? So AMT is a low frequency signal, and CT is a very high frequency signal we have for the modulation process. So yeah, here we are talking about on the frequency modulation. So the other parameter of the signal, such as amplitude, should always be kept constant here. So so this frequency modulation always be characterized in the angle modulation. If we talk about the carrier signal here, so carrier signal can be represented by either AC cos omega CT, right? So here we have amplitude. This one is AC, is the amplitude of the carrier signal, while omega CT is the angle of the carrier signal, total angle. So we can represent it or theta ct is equal to theta ct is equal to omega ct. So this one is the angle of the carrier signal. So we have here, so we can change the angle with by varying the frequency of the carrier signal here. So if we varying the frequency of the carrier signal with in accordance with the instantaneous value of the modulating signal or massive signal, then we have a frequency modulation here. So that's only the case we will discuss in the further study. Now, if I talk about the phase modulation, so what is the phase modulation? In the phase modulation, the phase of the carrier signal is directly varied in accordance with the instantaneous value of the massive signal here. So, and the rest of the parameters such as amplitude should be kept constant. So this is about the phase modulation here. Now, the frequency modulation here. Actually, we are talking about only the frequency, as in the last slide, last PPT, we had seen that theta 80, theta ct. I want. So theta ct is equal to omega ct, or we can write 2 pi fct. So here we want to change or vary the frequency of carrier signal. So the instantaneous value of the carrier signal is changed by using this equation. This is FIT, where FIT is the instantaneous frequency of the carrier signal. Here is the FC plus KFMT. Here FC is the frequency of the actual carrier signal and MT is the massive signal here, right? So, so you can see this carrier frequency is varied in accordance with the instantaneous value of the massive signal. Here kf is the sensitivity factor, so we can call the frequency sensitivity factor for the frequency modulation here, right? So and the unit for the kf is always be hertz per volt. You can see here hertz per volt. So in terms of phase, we can write this equation in the form of, I can change this equation in the form of theta it, instantaneous value of the angle at particular frequencies. So theta it is the instantaneous value of the angle. So here you can see we need to take the integration of this equation. So we have this one equation now, 2 pi fct plus 2 pi kf 0 to t mt and dt. So here you can see we have to do the integration of the massive signal. So finally we have the frequency modulated signal equation by putting this equation in the this AC cos theta it. So we have to put this theta it here. Now we by putting this equation from this to this, we have the frequency modulated signal equation by this one. So AC cos 2 pi fct and 2 pi kf 0 to t mt dt. So you can see here the carrier frequency is modulated or varied in accordance with the instantaneous value of the massive signal here. So the next one, so this is the main, so we can say this one is the main frequency modulated equation. This is important, and we have to remember this equation as well for the analysis or for doing the numerical section of this frequency modulation. This is the most important equation here. Now the relationship between PM and FM. So PM means phase modulation and frequency modulation. Here modulating wave means massive signal, we can say modulated signal is also known as the message signal. We have to apply this message signal to the integrator and then apply to the phase modulator. Then we have a frequency modulated wave, right? Why? Because first this message signal has to be passed from the integrator. That's why after passing through the integrator, we have this equation where we have a frequency modulation. And if we have the another message signal and we want to make the frequency modulation, so we have to pass this message signal from the differentiator. Then if we apply this differentiated signal to the frequency modulator, then we have PM or phase modulated signal as well. So here you can observe here in the relationship between PM and FM. For FM, uh, uh, so this is a relationship we can have. So through the PM, we can also achieve the frequency modulated signal, and through the frequency modulated signal, we have the phase modulated signal. So we can say phase modulated and frequency. In both the cases, we have the variation in the frequency. So this is the relationship between PM and FM. Now the waveforms here, we can see this one. The first one is the carrier signal, and the second one is a sinusoidal modulated signal, that we can say the modulating signal or message signal as well. So this carrier signal always be varied in accordance with the instantaneous value of the message signal. If the message value is increasing, then the variation or deviation in the carrier signal will be more. If the signal is varied less, then the variation or deviation in the carrier signal will be less. So here we can see, here we have the amplitude variation in the carrier signal. So we can say this is a amplitude modulated signal here, right? Because here you can clearly see here the maximum value of message signal. That's why we have the maximum deviation in the carrier signal amplitude the maximum deviation in the amplitude of the carrier signal will be more uh, at the maximum value of the message signal, while at the minimum value of the message signal we have the less value of amplitude of the carrier signal. Now, if we talk about the frequency in last two signals D and D, we have the frequency variation, but only the thing is here the frequency variation is high at the maximum value of the modulating signal. Here the frequency variation is high at the maximum value of the modulating signal in the case of E. And at the minimum value of the message signal, we have the less frequency compared to the maximum frequency. So we can say this one is the frequency modulated signal, while in the case of D, we have the maximum variation at the low value of the low value of the message signal, and the high at the high value of message signal we have the less variation. So we can say there is a 90-degree phase shift in between these two, D and D. So we can first to have in other words we can say that to have the frequency modulation in that side, as we had discussed here, to have the frequency modulation, first we have to do the differentiator of the message signal, then we have passed this signal through the frequency modulation, then we have the phase modulation signal. So if we pass this signal through the if first we have to take the differentiator of this signal. If we consider this signal as a cosine variation, and if we take the differentiator of this signal, then we have the sine variation. Means there will always be 90-degree phase shift after taking the differentiator. That's why the only the change in the high and low frequency is only the 90-degree phase shift. So we can say this one is the frequency modulated signal here. So as we have mentioned here, the first one is the carrier signal, modulated signal, massive signal, AM signal, PM signal, and FM signal. I hope these all the frequency waveforms of related modulation techniques is clear to all of you. Now talking about the here, we are talking about the FM signal. Theta 80 meter instantaneous of the FM signal is obtained by this equation as if I take the integration of 0 to 2 fi dt, so we have the final equation 2 pi fct delta fi fm sine 2 pi fmt. So the delta fi fm is known as beta, the modulation index of frequency modulation. So this one is the modulation index. Now the main equation, now we will do the analysis of the fm, right? So this equation we already have discussed in the last slide. 2 pi fct, theta is instantaneous value of the angle of the modulated signal, and where we have theta it is equal to 2 pi fct. This one is beta is the modulation index of FM signal, as we all have already told to you. Now beta, it is represented by beta delta fi fm. Now this equation will become 2 pi fct plus beta sine 2 pi fmt, right? If I put this equation in the main AC cos theta it, if we put this theta it into this equation, then we have the frequency modulated signal, this one, right? So here you can observe here 2 pi fct plus beta sine 2 pi fmt, right? So there will be two cases for the frequency modulation. If the value of beta is very less than 1, then we can say this one narrowband fm, while if beta is very greater than 1, then we can consider this one as wideband fm, right? I think this one is clear to all of you. Now, wideband FM, the equation for the wideband FM, in generally we have this equation ST is equals to pi FCT, as we have already discussed here, 2 pi f beta sine 2 pi FMT, right? So this equation we can write in other form by using the Euler theorem, or we can say this is a real part, because this is a cos term. So we can say this is a real part of AC e to the power complex value of 2 j2 pi fct plus j beta sine 2 pi fmt. So we can say here, or we can represent this equation in this form as well. So here, as I this one is represent the this sign is represent the periodic nature of the signal, right? So this one is the periodic nature of the signal. AC exponential of j beta sine 2 pi fmt is complex envelope, and this one is a periodic function, right? If this one is the periodic function, from the periodicity property, we have st as st plus k tm is equal to uh, st plus k by fm, where tm is equal to time period is equal to tm is equal to 1 by fm, as we have the modulated frequency is fm. So time period will always be 1 by fm. So because this signal is a periodic signal, so to have the frequency spectrum, we need to do the Fourier analysis, Fourier series. So this is the exponential Fourier series equation to find the Fourier coefficient of the given equation. And by using this equation, and here the Cn is the Fourier coefficient, and value of the Cn is equal to Fm. This one is Fm minus T by 2, because T is equal to 1 by Fm. So we have, because integration of minus T by 2 to T by 2, right? 1 by T. So T is equal to 1 by Fm here. So we can replace this T from this one. So we have this equation here. Now, by solving this equation, we have this one we have this one form of Cn, right? And I know, and we know, we are aware about the Bessel function equation, and this equation is very much similar to the Bessel function. And nth order Bessel function of the first kind is given by this one. So you can correlate this one. These both equations are looking like same. So we can say Cn is equal to always be AC, Gn, beta, and we can place this we can place this Cn value in this equation, and we have the equation of periodic function A S bar t is equal to AC j and beta exponential of j 2 pi and fmt. Now we have to move towards the final equation of wideband fm. So by putting the main equation of s bar t, we have this final equation. I think this one is clear to all of you how it comes, right? So after taking the frequency transform of this equation, we have this equation. Now you can clearly observe here, we have the uh, NFM terms here, mean uh, the the bandwidth of the here f is equal to fc plus minus n fm, and n is equal to 0 to 0, 1, 2, 3. So you can clearly observe, if I put n is equal to 1, 2, 3, 4, 5 up to infinity, so we have the bandwidth of this signal is a minus infinity to infinity, or we have the bandwidth is equal to infinity. So in ideal case, the bandwidth of fm would be equal to infinity. Now, property of singleton FM for arbitrary modulation index beta. This one is a property. I think this one is already known to you. So, J and beta is equal to this is even property here. N is equal to minus n. So, even property always says that x minus t is equal to xt, as we know. X minus t is equal to minus xt for the case of odd property. Here always with a singular can we have, if n is replaced by minus n and minus n we have here. If the in terms of beta, j0 beta always the one you can already see here, beta by 2, and this one is the important property. All are the important property, but this one is the most important property to further analysis. That means the summation of is equal to minus infinity to infinity jn square beta is equal to 1. We can say this one is energy of the Bessel function as well. So, so in terms of power, average power, we have this equation. I think in amplitude modulation techniques, we already know how to calculate the average value. So we can directly see this AC square by 2. And for the wideband signal, we need to include the Bessel function as well. And we know that this value always be equal to the 1. So finally, we have the average power of the wideband signal AC square by 2, which is equal to the carrier power of the actual carrier power of the signal, right? Uh, now I would like to tell you about how to calculate the practical bandwidth of the uh, frequency modulated signal. Ideal case, we have the value of bandwidth is infinity, but a scientist named of Carson has derived the formula to calculate the practical value of the frequency modulated signal. So this one is known as either Carson rule. So from the Carson rule, we have the bandwidth is this one, 2 times of delta f plus w, right? So I think this one is clear to all of you. How this one is also known as Carson rules. So this Carson rules always be done for the beta plus 1 order of Bessel function, right? So where d is equal to delta f by omega deviation, so this one is already known to all of you. So I think This is all about the frequency modulation technique. Here we have covered the wideband frequency modulation in detail here. So I think this topic is clear to all of you. If you have any questions, please, thank you to all of you.